All right, so this is for my game theory class. The reason I'm recording this is because of the coronavirus, and we're having all of our class online. And we use this textbook, Game Theory by Philip Strafen. If you're not in my class, I just want to encourage you, please purchase this book. This is an amazing book. I want to be faithful to academic fair use, and we're not supposed to use copyrighted material as our own, and it's not my own. And I do want to encourage you you'll see in this video how well chosen the examples are. Philip Strafen has written one of the most readable textbooks and has great examples. He has great illustrations. He also chooses very interesting applications from evolutionary biology to anthropology to philosophy and economics. Of course, he looks at John Nash's work. John Nash, if you're not familiar with him, check out the movie A Beautiful Mind. So Strafen explains to us that we're interested in situations where the players can communicate. And we want to look at what happens when one player can make a commitment to move first. So they talk to each other prior to the game, and a commitment allows a player to move first. For example, suppose that Rose calls Colin on her cell phone and says, "Hey, I'm choosing B." And then she hangs up and she refuses to communicate with him again. Well, that way she has made a commitment to move first. Now, an important consideration is how believable that commitment is, right? If Colin just doesn't believe her, then she's not actually moving first, right? She's got to have some way to make the commitment credible. But that's how it could work. Now, communication also allows for threats and promises. So we're going to look at a few examples of what happens when one player or the other moves first. If you're more interested, you can check out Schelling's paper from 1960. So game 14.1, what happens if the players move simultaneously? Well, this is actually a zero-sum game and has a mixed strategy solution. If you're in my class, you should pause the video here and you should verify that the value to Rose is 3/2 and Rose's strategy mixture is 5/8, 3/8, and Colin's strategy mixture is 1/2, 1/2. But suppose we have a way for a person to commit to making the first move, and let's assume that Rose goes first. Well, here's how you analyze that. You say, look, if Rose goes first, suppose she plays A. Well, if she plays A, then Colin's only two choices are getting a big negative score or getting 0. And so, of course, he chooses 0. Then we look at what happens if Rose plays B, and Colin is then choosing between a 1 and a big negative score, so he would choose this. So now we can see what Rose gets. If Rose chooses A, she gets the 0. She gets the x coordinate value. And if she chooses B, she gets this -1, this x coordinate value. So notice that Rose's value, when they moved simultaneously, Rose had a value of 3/2. But if she goes first, right, she ends up with this value of 0. So going first has been a problem. Well, what happens if Colin goes first? Well, taking a look at Colin A, Rose is choosing between 3 and -1, so she chooses A. And if Colin is choosing B, then Rose is choosing between a 0 and a 4. Well, of course she chooses the 4. So now Colin knows that if he plays A, he gets the -3. And if he plays B, he gets the -4, and he is not interested in losing, but he doesn't have a choice in this situation. So if Colin goes first, right, his value is -3, so Rose's is +3. So all three of these values are Rose's values. And since it's a zero-sum game, Colin is making the opposite. All right. But the key takeaway here is that when we switch to a player going first, it hurts them. Rose was making 3/2 when it was simultaneous. We switched to her being the first player, and now she's making 0. But if she gets to play second because Colin is playing first, then she actually improves from the 3/2 to 3. So Colin had a huge advantage when Rose is going first, and Rose would prefer that Colin goes first. Well, let's take a look at the second example. This is actually equivalent to the game of chicken, although I think that in the classic 1950s style chicken where their race cars are driving at each other, those ought to be big negative outcomes like -10, -10. But this game has all the right dynamics, and we can look at its payoff polygon. And when you solve this game, we've solved it before, but looking at this game, there are 3 Pareto optimal outcomes. And but it doesn't settle down. There are 2 saddles. The corners here are saddles, but Colin prefers being further north and Rose prefers being further east, so they would argue over this. An outside observer might say that this 3-3 outcome is the best one, but they're going to argue over that. So we have 2 saddle points, and the problem is that they're not equivalent and interchangeable. So it's hard to know what to do with this game. So let's talk about what happens if one of the players gets to go first. Well, check out what happens for Rose. If Rose says, I'm playing A, then Colin's choosing between 3 and 4. He picks option B. So Rose only gets 2, but what if she chooses B? Well, then Colin's choosing between 2 and 1. He'll choose the 2. And if Rose gets to go first, her value is 4. She gets to commit to B first, and then Colin is stuck playing A, right? And the exact opposite things happens. If Colin goes first, he says, I'm playing B. And Rose is stuck playing A, and she only gets 2. All right, so that's interesting. Let's take a look at game 14.3. So now I want you to notice the dominance, right? That 2 is better than 1, so Rose would always choose to play A if Colin is playing A, but she'd also always choose to play A if Colin were playing B. So here, Rose A dominates Rose B. So all Colin is looking at is, hey, I could either get 3 or 1, so this non-zero sum game is solvable in the strict sense, and it has a saddle that's Pareto optimal at this point 2, 3. Excuse me, we have a saddle that's not Pareto optimal. Notice that the 3, 4 is what makes the point 2, 3 Pareto inferior. Let's take a look at the geometry though. So here you can see the saddle point is not Pareto optimal. The Pareto optimal points are along the northeast boundary. But they're going to play the saddle point if they have to play simultaneously. Let's see how this changes, however, if Rose gets to play first. So what happens if Rose goes first? Well, again, we're looking at A, where Colin is choosing between 3 and 1. He chooses the 3. Then we check out what happens if Rose goes first and plays B, and then Colin is choosing between 2 and 4. So Rose gets to choose between the 2 circles, and she'll choose the value of 3. Okay? So she'll get her preferred outcome of 3, 4. Okay? What happens if Colin goes first? Well, if Colin goes first, strangely, he does worse. So let me make a note of this point. So if Rose goes first, the value of the game is 3, 4. okay? And remember that if they play this simultaneously, because of the dominance of row A, we had this saddle point, and the value was 2, 3. So allowing rows to go first has made rows better off. But let's check out what happens when Colin goes first. So if Colin chooses A, Rose is choosing between 2 and 1. So of course she chooses the larger value. And if Colin plays B, then Rose is choosing between 3 and 4. And of course she chooses 4. But now Colin's choosing between the 3 and the 1, so he chooses the original solution. So if he goes first, he's no better off. He just gets the same thing. So interesting, in this game, both players want Rose to go first, right? Rose wants to go first because she improves from 2 to 3. Colin wants Rose to go first because if he goes first, he still gets the saddle point value 2, 3. He does better if Rose goes first, so both players want Rose to go first. In part 2, I'm going to look at threats and promises.